So today let's discuss questions related to topic sequences in real analysis. There were only 5 to 6 questions asked on this topic, so let's just see them one by one. So question 1 says that prove that every bounded and a monotonically increasing sequence is convergent, and we are also supposed to prove that it converges to its least upper bound. Least upper bound is basically supremum of the sequence. So let us assume a sequence that is bounded and monotonically increasing. So let Sn be a sequence and let it be bounded and monotonically increasing. Monotonically increasing. Now let S be the range of the sequence. Let S be range of sequence. Since the sequence is bounded, its range is also bounded. So from here we can say that S is also bounded. And by completeness property, every bounded set attains its supremum or the least upper bound. So by completeness property, S has a least upper bound or supremum. So let us assume something. Let us assume that a supremum of S is equals to, let's say, M. Now we are supposed to show that our sequence Sn is basically converging to this number M. So what is our claim now? So we are supposed to prove now that the sequence Sn is converging to M as n approaches infinity. So let's see how we can show that. Now since the range set is bounded by M, the sequence is also bounded by M. So this M acts as upper bound of sequence. So if M is upper bound of sequence, also it's a least upper bound. Let me write it here. So it's a least upper bound. So any number less than this M will not be an upper bound of sequence Sn. So any M minus epsilon for any epsilon greater than 0 will not be its upper bound, will not be upper bound of sequence Sn. So if that's the case, then there must exist some term from sequence Sn that is greater than this M minus epsilon. So that means that there exists some M such that Sm is greater than basically M minus epsilon, but we know that our sequence Sn is monotonically increasing, but Sn is monotonically increasing sequence. So what that means is Sn is greater than or equals to Sm for all n greater than or equals to M. That is meaning of a monotonically increasing sequence. That means as we increase index, the sequence term also increases. So if that's the case, then if I combine these two, let's name this as 1 and this sequence as 2. So from here I will get that M minus epsilon is less than Sn for all n those are greater than this M, this term, this index M. So, and we know that let's name this as equation 3, and we know that M is basically upper bound or supremum of sequence Sn. So that means that Sn is less than equals to less than m. We don't know whether this m will be attained or not, so let's do it less than capital M only. And this term is less than m plus epsilon, because if m is an upper bound, then m plus epsilon is also an upper bound, because m plus epsilon is greater than m. So if I combine these terms, equation 3 and equation form 4, so what I'll get is m minus epsilon is less than Sn, which is further less than m plus epsilon, and this holds for all n, those are greater than m. So this can be written as minus epsilon is less than Sn minus m less than epsilon, and it holds for all n, those are greater than m. So this is equals to absolute value of Sn minus m is less than epsilon for all n greater than m. So this basically is, if you observe that, it is basically the definition of convergence. So from here we have shown that the sequence Sn is convergent and it's converging to its least upper bound. Now similar question can be formed about a monotonically decreasing sequence, and that will converge to basically its greatest lower bound. And you can prove it in similar format, like you can assume its greatest upper bound as m, and then if m is greater upper bound, then any number greater than m will not act as its upper bound, so there will exist some term. So the proof is exactly on similar lines, so you can try that for yourself. So let's move on to see the next question. So this question says that prove that the sequence an, which is satisfying this condition. So there is a sequence an and it's satisfying this condition, that is an plus 1 minus an is less than or equals to epsilon times an minus 1. And here alpha is basically lying in between 0 to 1. And this holds for all natural number, those are greater than 0, greater than 2. So we are supposed to prove that an is basically a Cauchy sequence. So our claim is an is a Cauchy sequence. Let's see how we can show that. So first let's just see what is definition of a Cauchy sequence. So a sequence Sn is said to be Cauchy if for each epsilon, like no matter what value of epsilon we choose, each epsilon greater than 0, there exists a positive integer m, such that Snp minus Sn is less than epsilon for all n greater than equals to m, and this p can take any value, that is p can take any value greater than 1, or p belongs to natural number, you can write that as well. So this means that difference between any two terms of a sequence, if that difference is arbitrarily small for some n number that is greater than a certain stage, then we say that the sequence is basically our Cauchy sequence. Now let's see how we can use the given information. So it is given to us that modulus of an plus 1 minus an is less than or equals to alpha times modulus of an minus 1. Now if you observe that, it is true for all n, those are greater than or equals to 2. So I can apply similar relation for this one as well. Like for this term as well, I can use similar relation. So what I'll get is this is less than alpha and this will be less than alpha times modulus of an minus 1 minus an minus 2. That is basically alpha square modulus of an minus 1 minus an minus 2. Likewise, I can use similar relation on this term as well, and so on. So let's see what we'll get. So this term will be less than equals to alpha cube modulus of an minus 2 minus an minus 3. Now if you keep on doing this same thing again and again, so you'll reach a stage that you'll get alpha n less than equals to a1 minus a naught. Now how will you observe that, like whatever term we are getting here is basically the power of this number alpha. So to reach a naught, so a naught will be basically equals to a n minus n. So here we'll get, at the end step we'll get alpha raised n modulus of a1 minus a naught, because this term is, like the index of this term is 1 greater than index of this term. So this is what we'll get. Now if you observe that this holds for all n, so now let's use definition of Cauchy sequence. Let's name this as 1, and the definition of Cauchy sequence, for definition of Cauchy sequence, let's assume that alpha is greater than 0 and it is given to us, and p is also greater than 1. So modulus of a n plus p minus a n will be equals to, I can write this as a n plus p minus a n plus p minus 1 plus a n plus p minus 1, and so on up till minus of a n plus 1 plus a n plus 1 minus a n. So what I have done is I have added and subtracted all the terms that lies in between these two terms. Now if I apply triangle inequality here, so using triangle inequality, what I'll get is modulus of a n plus p minus a n is less than equals to modulus of a n plus p minus a n plus p minus 1 plus modulus of a n plus p minus 1 minus a n plus p minus 2, and so on up till modulus of a n plus 1 minus a n. Now for each term you see that the difference between the index of each term is 1 only, like it is a n plus p and this is a n plus p minus 1. Likewise for each modulus terms. So in each of these terms we can apply the relation that we got from equation number 1, that is modulus of a n plus 1 minus a n is less than alpha n modulus of a1 minus a naught. So this term will be less than equals to alpha raised n plus p minus 1 modulus of a1 minus a naught plus alpha raised n plus p minus 2 modulus of a1 minus a naught up till alpha n modulus of a1 minus a naught. And I can just write this term as this: alpha raised n plus p minus 1 plus alpha raised n plus p minus 2 up till alpha n times modulus of a1 minus a naught. Now observe that since p is greater than or equals to 1, so n plus p minus 1 is greater than or equals to n, right? So what I can do is I can just take alpha raised n as common. So what I'll get is alpha raised n alpha raised p minus 1 plus alpha raised p minus 2 up till alpha plus 1 times modulus of a1 minus a naught. Now this is a GP series because alpha is given to us as, they have given us that alpha lies in between 0 to 1. So this term will be equals to alpha raised n 1 minus alpha raised p divided by 1 minus alpha times modulus of a1 minus a naught. Now if I take n approaches infinity, then this term, that is alpha raised n, will approach 0 because alpha lies in between 0 to 1. So from here I got that a raised n plus p minus a raised n approaches 0 as n approaches infinity. And if it approaches 0, that means that their difference is basically arbitrarily small. and we have chosen our epsilon greater than 0, so we can write it like this as well. So we got that our sequence Sn is a Cauchy sequence. Now let's move on to see the next question. So this question says that they have given us a sequence whose first term is 2, so x1 is equals to 2, and other terms hold this relation, that is xn plus 1 is equals to square root of xn plus 20, and this holds for all n equals to 1, 2, 3 and so on. So we are supposed to show that the sequence is convergent. So our claim is xn is a convergent sequence. Now let's see its behavior first. So x1 is equals to 2. So what will be my x2? It will be equals to square root of 2 plus 20. And we know that 2 is less than 5. So 2 plus 20 is less than 5 plus 20. So from here I'll get my x2 as less than equals to square root of 5 plus 20, that is 25, and square root of 25 is 5. So from here I got that my x2 is less than 5. Likewise, if I calculate my x3, it will be square root of x2 plus 20. But since x2 is less than 5, so x2 plus 20 will be less than square root of 5 plus 20, that is again 5. So from here I got that my third term, that is x3, is also less than 5. Now if I assume that let's use induction to show that all the terms of sequences are basically less than 5. So let x raised n minus 1 is less than 5. Now if I just add on 20 on both the sides, so I'll get xn minus 1 plus 20 will be less than 5 plus 20. Now if I just take the square root, so it will be square root of xn minus 1 plus 20 and less than 5 plus 20, that is 25. So, and observe that this is basically xn term, so we got it as less than 5. So our sequence xn is a bounded sequence or bounded above sequence. Now if we show that it is monotonically increasing as well, then we can use the first relation that we proved, that is if a sequence is bounded and monotonically increases, then it converges to its least upper bound. So let's see how we can show that it is a monotonically increasing sequence. So the first term is x1 is 2, and if we calculate x2, it will be square root of 2 plus 20, that is square root of 22. Now let's just use calculator to see what will be square root of 22. You can observe that it will lie somewhere between 4 and 5. So it is 4.69. So it is greater than our x1. Now if I calculate my x3, so that will be square root of x2 plus 20, that is square root of, let's say, 4.69 plus 20. I'm just getting an idea whether it is an increasing sequence or not. It will be somewhere close to 25. So it is basically 4.96, which is again greater than x2. So the increasing relation holds for certain, quite initial few terms. So let us assume that xm minus 1 is less than xm. Now we'll show that xm is less than xn plus 1. So if I just add in this 20 on both the sides, so I'll get xn minus 1 plus 20 less than xm plus 20. Now if I just take the square root, so I'll get xm minus 1 plus 20 less than square root of xm plus 20, and this is basically xm and this is xm plus 1. So we got that our sequence xn is a monotonically increasing sequence. So also earlier we have shown that it is a bounded sequence as well. So our sequence xn is monotonically increasing sequence and bounded above as well. Bounded above as. So this basically shows that, so using the relation, like we have shown the prove this relation, so this gives us that our sequence xn is convergent and it converges to its least upper bound, or that is supremum of sequence. I guess we are not supposed to find its limit, we are just supposed to show that it's convergent. Now even if they ask us to find the limit, we can do that as well. So let's assume that supremum is, let us assume that supremum of sequence xn is equals to m. So since the sequence, whole sequence is convergent, so it's every subsequence is also convergent. So we'll get m equals to square root of m plus 20. So that will give me m square minus m minus 20 equals to 0. And this is basically a quadratic relation in m, so we can just solve it for m. So my m will be 1 plus minus square root of 1 square minus 4 times minus 20 divided by 2. That is equals to 1 plus minus square root of 81 by 2, that is equals to 1 plus minus 9 by 2. So this give me m as either 5 or my m as minus 4. But observe that all the terms of our sequence are positive only. So this will also converge to a positive limit because all sequences are positive. So we can just discard this option, that is m equals to minus 4. So our sequence converges to this, m equals to 5. Now let's move on to see the next question. So the next question says that we have two sequences xn and yn, and these are defined inductively like this. Like the first term of xn and yn are given and there's a relation given in between other terms. So we're supposed to show this relation. That means that xn is increasing sequence but yn is a decreasing sequence, and all terms of xn are less than terms of yn. And also we are supposed to show that both the sequence converge to same limit L, where L lies in between these two terms. Okay, so let's do that. Let's see how we can do that. So first thing that you should observe in this sequence is, observe that the sequence xn, that is given to us as square root of xn minus 1 and yn minus 1. So if you observe that this is basically geometric progression or geometric mean of xn minus 1 and yn minus 1. So xn is defined as geometric mean of xn minus 1 and yn minus 1. Geometric mean. Now observe the relation of yn. So yn is defined as 1 by yn is equals to 1 by 2, 1 divided by xn plus 1 divided by yn minus 1. This is basically harmonic mean of these two terms, that is xn and yn minus 1. So, and we have like for similar terms, like had it been for xn minus 1 and yn minus 1, then for similar terms there is a relation in between geometric mean, harmonic mean and arithmetic mean, and that comes handy in solving many questions of sequences. So you must remember that harmonic mean, that I am representing harmonic mean with HF, is less than geometric mean, which is less than arithmetic mean. Here H is for harmonic mean, G is for geometric mean and A is for arithmetic mean. So remember this relation, it comes handy while solving many questions in sequences. Now let's see this question. So in this question, x1 is basically 1 by 2 and y1 is 1. So if I calculate x2 from here, so that will be square root of x1 y1. So it will be square root of 1 by 2, and if you solve it you'll get somewhere like around 0.7 something, and observe that it is greater than x1. So from here I got that my x2 is greater than x1. Now if I calculate y2, so I'll get my 1 by y2 as 1 by 2 times 1 by x2 plus 1 by y1. My y1 is 1, I guess. Yeah, so it will be 1 by y2 will be equals to 1 by 2, and from here x2 will be square root of 2 plus 1. And if you'll solve this, let's see what it is, 1.4 something, so it is 2.4 something, so it is 1.2 something. So from here I will get your y2 as, let's just do approximation sign, so y2 will be 1 divided by 1.2 something, so this will be less than 1, which is equals to y1. So from here you got that your y2 is less than y1. Now since our x1 is less than y1 and we got that our x2 which is greater than x1, this turns out to be 0.7 something, and if you calculate your y1 y2, let's see what we get. Let me just use calculator to see what exactly it is. So your y2 will be somewhere around 0.28. So let me just write it. So it is somewhere y2 is approximated to 0.828. Now observe that y2 is greater than x2, that is 0.7. So y2 is, and y2 is less than y1. So we have proved the required relation for n equals to 2. So that is x of 1 is less than x of 2, which is less than y of 2, less than y of 1. So we have proved this relation for n equals to 2. Now we are supposed to prove it for all n. Let's see how we can do that. Now we'll be basically using a induction to solve it for general. So let us assume that x of n minus 1 is less than y of n minus 1. So if that's the case, then its geometric mean will be xn will be equals to square root of xn minus 1 times yn minus 1. And we know that like for two numbers, geometric mean lies in between those two numbers. So from here we'll get that xn minus 1 is less than xn, which is less than y of n minus 1. Now let's name this relation as star 1 for time being. Now take relation in between and now take these two terms, that is xn is less than yn minus 1. Now if you take their harmonic mean, let's yn will be basically harmonic mean of xn comma yn minus 1. Now again harmonic mean of two terms lies in between those two terms, so from there we'll get that xn will be less than yn, which is less than yn minus 1. Let's name this as star 2. Now if we just combine star 1 and star 2, combining star 1 and star 2, what I'll get is xn minus 1 is less than xn, which is less than yn, which in terms is less than yn minus 1. And since here n is arbitrary, we haven't chosen any fixed n, so it holds for all n equals to 2, 3 and so on. So this basically proved our relation, and from here we got that our sequence xn is monotonically increasing and also it's bounded above by, let's say, y1, that is 1, because it's bounded above by sequence yn, and like the upper bound of sequence of yn is 1, so we are taking that only. Likewise we got that our sequence yn is monotonically decreasing and bounded below. And it's bounded below by sequence xn. So we can say that it's bounded by first term of sequence xn, that is 1 by 2. So because we are doing this because like x1 is 1 by 2, which is less than x2, less than x3, and so on up till xn, which in terms is less than yn minus 1, and so on up till y1, which is equals to 1. So from here we got this as lower bound for yn sequence and this as upper bound for xn sequence. So now let us assume that a sequence xn is converging to, let xn converges to L and yn converges to M as n approaches infinity. Now if we use both the recursive relations that are given to us, we'll get that L is equals to square root of Lm and 1 by m is equals to 1 by 2, 1 by L plus 1 by m. Now if you solve these two terms, what you'll get is L square is equals to Lm and 1 by m is equals to 1 by 2L plus 1 by 2m, and that basically simplifies to L equals to 0 or L equals to m, and from here we'll get 1 by 2m is equals to 1 by 2L, that is L equals to m. Now since all the terms of sequences, like both the sequence lies in between 1 by 2 and 1, that is the sequence is basically a sequence of positive terms, so it cannot converge to 0. Also that can be observed from this as well, because like the sequence xn converges to its least upper bound, and its least upper bound has to be somewhere less than 1, and sequence yn will converge to its greatest lower bound, and its greatest lower bound will be something more than 1 by 2. So the sequence converges in between these two terms. So from here we got that we can discard this option. So from here we got that our L is equals to m, where L is basically converging limit of sequence xn and m is our converging limit of sequence yn. And we have proved that the sequence, like the limit lies in between, see L and m lies in between 1 by 2 and 1. Because of this least upper bound and greatest lower bound thing, we got this. Now let's move on to see the next question. So the next question says that discuss the convergence of this sequence xn, and where xn is defined as sine of n pi by 2 divided by 8, and here n is taking values from natural numbers. So let's see first few terms and observe how the sequence is behaving. So x1 will be equals to sine pi by 2 divided by 8, which is equals to 1 by 8, and x2 will be sine pi divided by 8, which will be equals to sine pi is 0, so it is 0. x3 will be sine 3 pi by 2 divided by 8, and sine 3 pi by 2 is minus 1, so it will be minus 1 by 8. Likewise my x4 will be sine 2 pi divided by 8, and sine 2 pi is 0, so it will be 0. x5 will be sine 5 pi by 2 divided by 8, and I can write my sine 5 pi by 2 as sine 2 pi plus pi by 2, and sine 2 pi plus theta is basically sine theta only, so it will be sine pi by 2 divided by 8, which will be equals to 1 by 8. So if you observe that, let's just calculate a quite few terms, like few more terms. So x6 will be equals to sine 3 pi divided by 8, which is again 0. x7 will be equals to sine 7 pi by 2 divided by 8, and sine 7 pi by 2 is same as sine 3 pi by 2 divided by 8, which is minus 1 by 8, and x8 will be equals to sine 4 pi divided by 8, which is 0. Now if you observe that our sequence is basically oscillating in between three numbers, that is 1 by 8, 0 and this minus of 1 by 8. So this is basically our, if it is 1 by 8 and this is minus 1 by 8, so it is like moving like this. So it is a oscillatory sequence, you can observe that from here, and so therefore it will have more than one convergent subsequence, and those are converging to different limits. So that is limit as n approaches infinity, xn will be equals to 0. Observe that it is equals to 0 when n is a even number. So when n is even, and it is equals to 1 by 8 at x1 and then x5 and then x9 and so on. So it is equals to 1 by 8 when n equals to 4m plus 1, and here m belongs to natural number union 0, and it is equals to minus 1 by 8 when n equals to 4m plus 3, where m belongs to natural number union 0, because only when we include 0 as index, then only we can say n will take 1 and 3 as values. So this is a limit, this is a basically the range set. So from here we get that xn is an oscillatory sequence and its limit is not unique. Its limit is not unique. So sequence xn is not convergent. Now let's move on to see the next question. So the next question says that they have given us a sequence xn which is defined as like this, and we're supposed to show that the sequence converges to this limit. In the question they have specifically mentioned that show it's converging, like show the point as well where it converges. So let's see how we can do that. Now first let's see behavior of sequence xn. So x1 is equals to 5, therefore my xn plus 1, and xn plus 1 is defined as square root of 4 plus xn. Now from here if I calculate my x2, so that will be square root of 4 plus 5, that is 3. Now observe that x2 is less than x1. Now this basically give me hint that the sequence can be a decreasing sequence. So let's see. So if I assume that my xn minus 1 is less than xn, so from here I will get that 4 plus xn minus 1 is less than 4 plus xn, and if I take its square root, it will be square root of 4xn minus 1 less than square root of 4 plus xn, and this is basically xn term which is less than xn plus 1. So using induction we got that, using induction we got that sequence xn is a decreasing sequence. Now let's see if it has a lower bound as well, because then we can just directly use the theorem that if a sequence is monotonically decreasing and is bounded below, then it converges to its lim, so greatest lower bound, that is limit. So observe that I got my x2 as square root of x1 plus 4, that is equals to square root of 5 plus 4 which is 3, and it is greater than x1. Oh, it is less than x1 because our x1 is 5. Now if I calculate my x3, so it will be square root of x2 plus 4, that is equals to square root of 3 plus 4, which is greater than square root of 4, right? Because 3 is greater than 0, so I can do this, and square root of 4 is 2. So from here I got that my x3 is greater than 2. Likewise, if I take, let me take that xk is greater than 2, then from here I'll get that xk plus 4 will be greater than 2 plus 4, which is also greater than 4. So from here I got that xk plus 4 is greater than 4. Now if I take its square root, it will give me square root of xk plus 4 is greater than square root of 4. And this is term for xk plus 1. So this gives me xk plus 1 is greater than 2. So from here I got that by mathematical induction, I got that xk plus 1 is greater than 2. So my sequence xn is bounded below and monotonically decreasing. So by the result we got that it converges. So it converges to its greatest lower bound. So let us assume that it's L. By completeness property it will always exist because it is bounded below. So let infimum of sequence xn is equals to L. Now if it converges to L, so my L should equals to square root of L plus 4, because if it converges then all its subsequence converges. So from here we got that L square minus n minus 4 is equals to 0, and it is basically a quadratic equation in L. So I can just solve it for L. So L will be 1 plus minus square root of b square, that is minus 1 square minus 4 a times c, and it will be equals to divided by 2. So it will be equals to 1 plus minus square root of 1 plus 16 divided by 2. So from here I got my L as 1 plus minus square root of 17 by 2. Now if you observe that our sequence is bounded below by 2, so all the terms are greater than 2 only, right? So it cannot take negative limits because all the terms are greater than 2. That means that all the terms are positive only, so we can just discard the negative limit. So from here L is equals to 1 plus square root of 17 by 2. We discarded negative limit because sequence is of positive terms, and sequence of a positive terms converge to a positive number only. So please, so it converges to a positive number only. So that completes our question on sequences. There were only these many questions asked on this topic. So thank you for watching, and please do like, share and subscribe the channel. Thank you.